We can derive the equations that we need to solve problems in fluid flow by addressing mass and momentum conservation. So we'll start with generic equations for conservation of any species, and that will be written like this. So the term on the left is the source, and then the divergence of the flux plus the change in the rate of change of storage, where S is a source, this is flux of the quantity that we're conserving, and C is the dependent variable, cap theta per unit volume, where this is what we conserve. So for mass conservation, cap theta is mass. So C is cap theta per volume, and that's mass per, this is the total volume now, and that's the density of the fluid. So that's going to be our dependent variable. We can do the storage term just straight away. That's the rate of change of C, and so for our application, that's just the rate of change of the density. Okay, so that gives us that term. Now, the flux, that has an advective term, which we'll say is A, and a diffusive term in general. For the conservation of mass of the fluid, the diffusive term will set equal to 0. The advective term, in general, the advective term is going to be equal to the flow velocity times C, or that should be C. So for our problem, it's the velocity times the density. Okay, that gives us advection, and we can, let's see, so this would be flux, and we got diffusive flux for this problem is equal to 0, and then storage, this would be a case where mass is produced from within the volume, within a control volume. That's going to be, well, it's potentially possible. Most of the time we won't include that kind of process, but let's just say that for completeness we have some kind of mass source that we'll call M. And so then our conservation equation is just formed by substitution. So the conservation of mass would be this source term times the divergence of the flux, which is just advective flux here. So that's going to be the fluid velocity times the density, and then the rate of change of the density with time. Now the next step is to derive an equation for the conservation of momentum. So for this case, cap theta is going to be momentum, which we'll say is mass times velocity, and so the variable C is the variable that we're conserving, mass times velocity per unit volume, and these terms here give us the density. So the variable C is the mass times the velocity. And so now we can go ahead and develop the individual terms for the conservation equation. Storage is dc dt, and that's going to be just by substitution. And flux, we've got advection and diffusion. And in this case, we say that the advection, well, in general, the advection will be equal to the velocity times c. So in this case, it's velocity times the density. Okay, now in the case of the diffusive flux of momentum, that's going to be equal to the stress within the fluid. So I'll use sigma to mean the stress tensor, and then we can also recognize that we'll have source, and the source we'll just call, in many applications, F will end up being the unit weight of the fluid, which will create a body force, which will create like hydrostatic pressure, but we'll just keep it as a generic F for now. So we can substitute this to give the governing equation. So, well, let's resist labeling it. Let's just do the substitution, and we'll call it F. One is this velocity times density, and the other one is minus the stresses in the fluid. And then we also can include the storage term, which is the rate of change of the product of velocity and density. Okay, so there's our first cut at the conservation equation for momentum in a fluid. Now, one thing that's often done is to simplify this, and the way we can do that is by recognizing this term here. Well, let's do a little bit of algebra here. So we write this as F, and then this divergence term I can distribute out like this. And I'm gonna write this term here like this with a product rule. Okay, so this term here, that expands out like this. Okay, so now what I want to be able to do is factor out or combine this term and this term. So I'm going to bring those over here, and I'm going to factor out this velocity, and then I'll get this. Okay, so that gives me that term, and then I have this one, which is this term, minus the divergence of the stresses, and plus this term here. Okay, all right, so now this term here, the divergence of the velocity times the density plus the rate of change of the density with time, if we come back up here to mass conservation, the term in parentheses that we just had is this. So if we say that there are no sources within the fluid, so this m term here is 0, then this is 0. Okay, and that allows us to get a somewhat simplified version of this equation, which is like so. Okay, what we've seen in our analysis so far is that we can use principles of conservation to come up with a momentum conservation equation on the left and a mass conservation equation on the right. Now, to proceed, we need to include the properties of the fluid in order to have a better understanding of this term here, the stress term. And so to do that, let's first develop a conceptual model for the stresses in the fluid. And that will be like this. So the stresses in the fluid will equal the pressure, or the mean stress, the average stress, plus some deviation from the mean stress. So pressure, that's going to be the average of the 3 normal stresses. And this delta sigma is the deviatoric stress, the difference from the mean stress. Okay, so I think conceptually that makes sense. The minus sign is needed here because of our convention for the signs of the stresses. What we're going to say is that a compressive stress is a stress that is less than 0. A tensile stress is a stress that is greater than 0. So if the pressure is increasing, if the fluid pressure is increasing, we usually think of an increase in compression, and so that's why we need that minus sign there. Okay, so this is our conceptual model. We're going to use what's called the constitutive equation for a linear viscous fluid, or for a Newtonian fluid, and it's going to look somewhat like our conceptual model. It's going to say that the stress tensor is like this. Sigma ij is equal to minus p times the Kronecker delta plus the viscosity times the gradient in the fluid velocities. Okay, so recall that that u is the velocity. So this is these are the shear strain rates here, and this is our at least this is one way to write this constitutive model for a Newtonian fluid. Now we can also write this using a couple of other forms. One way that you'll see it written is like this. Keep and we will add here, I'll write it like this. So these are equivalent, and to see how that works, what I'll do is write an example out like this. Okay, so that's going to be this nabla operator, which we'll write like this. I'm going to write it just in 2D because I think that's going to be sufficient for you to see how this works. So there's one, should be just one, and U2. So doing that operation out, we get, this gives us that matrix, and then if we take the transpose, we'll switch these two. And so I think that you can see hopefully now that these two forms are equivalent. Another way to write this is like this. We just recognize that this term here is 2 times the strain rate tensor, so we can write it like this. Let's just write it out all the way. Let's see, ij minus p times the Kronecker delta. Okay, so that's an even more compact way of writing this. So now what we need to do is say that, well, we understand what the stresses are, at least how we're going to define the stresses, and we want to put that into the momentum equation where the stresses appear. Okay, so we rewrite the momentum equation here. Now that we have the constitutive law for the Newtonian fluid, we can return to the momentum equation, which we wrote above like this, and we can substitute in. So what I'm going to do is use this form of the constitutive law right here, and that will give us this. Okay, so we're just about done. I'm going to rearrange this a little bit. First of all, let's expand out this term, and then, well, let's do it in a couple of steps. Do that first. So when we do this operation, because p is a scalar, we just get the gradient of p, and then we get minus, well, let's take the viscosity out. Okay, so now we want to do one more thing. We want to group these terms, and we'll write it like this. Over on this side, we'll bring the pressure gradient, and we'll bring this term here. So that becomes, and on the right hand side, we've got, okay. So that, I think, is a pretty good place to stop. This is the Navier Stokes equation for conservation of momentum with a Newtonian fluid as the constitutive fluid, and we've got these 5 terms here. This is covering body forces. This is pressure gradient. So let's see, body forces. Here, that's pressure gradient. And this is the strain rate, and so this is the stress term, and this is essentially stresses that result from the viscosity of the fluid. Viscous stresses. This term here, where we have velocity entering twice, this is an acceleration term. This will be what we'll call convective acceleration. And this term here is the rate of change of the velocity with time. So that's an actual acceleration. When the velocity is changing, and so that would be call that transient acceleration. Now that we have the constitutive law for the Newtonian fluid, we can return to the momentum equation, which we wrote above like this. And we can substitute in. So what I'm going to do is use this form of the constitutive law right here, and that will give us this. Okay, so we're just about done. I'm going to rearrange this a little bit. First of all, let's expand out this term, and then, well, let's do it in a couple of steps. Do that first. So when we do this operation, because p is a scalar, we just get the gradient of p, and then we get minus, well, let's take the viscosity out. Okay, so now we want to do one more thing. We want to group these terms, and we'll write it like this. Over on this side, we'll bring the pressure gradient, and we'll bring this term here. So that becomes and on the right hand side we've got okay. So that, I think, is a pretty good place to stop. This is the Navier Stokes equation for conservation of momentum with a Newtonian fluid as the constitutive fluid, and we've got these 5 terms here. This is covering body forces. This is pressure gradient. So let's see, body forces. Here, that's pressure gradient. And this is the strain rate, and so this is the stress term, and this is essentially stresses that result from the viscosity of the fluid. Viscous stresses. This term here, where we have velocity entering twice, this is an acceleration term. This will be what we'll call convective acceleration. And this term here is the rate of change of the velocity with time. So that's an actual acceleration. When velocity is changing, and so that would be we'll call that transient acceleration.